explanatory. U, because it stands for expected value. So in probability, expected value and mu mean the same thing. Right. So anyway, properties of Poisson. X represents the number of occurrences in a continuous interval. Mu is the expected value of occurrences in this interval. The conditions, probability of an occurrence is the same for any two intervals of equal length. The expected value of occurrences in an interval is proportional to the length of this interval. That's a lot of stuff that doesn't seem to really explain anything, so I'll have to kind of parse that in a minute. But it's pretty straightforward when we actually get down to the nitty-gritty of it. The occurrence or non-occurrence in any interval is independent of the occurrence or non-occurrence in any other interval. The probability of two or more occurrences in a very small interval is close to zero. Right? So the Poisson probability distribution. X represents the random variable that is the occurrences of the Poisson experiment in some interval, giving this relationship. All right, so it's again a lot of words that are not overly meaningful just yet. All right, but this is the formula that we're working off of. All right, and I'll explain a little bit more about that in a few minutes. All right, so E of X or mu represent the same thing, but if you want to make that an alpha, historically it actually started off as an alpha, so we could actually do that. But again, like I said before, I think it's better explained as a mu because mu in a probability distribution represents an expected value. Right? As it turns out, the variance in a probability distribution is also the same as the expected value, so that's a relationship that we could rely upon. Right? The key is really coming down to this idea that if we can figure out the mean and the variance, which indirectly is giving us the standard deviation, then we will have all the characteristics of a Poisson distribution. Now, the big question is, what would be the need for a Poisson distribution? The reality is it has to do more with rare events than anything else, right? So the example that I have here is, I think it's pretty indicative of something that should, in theory, be rare. Suppose the average number of car accidents on the highway in one day is 4. What's the probability of no car accidents? That would be a typo, right? What is the probability of no car accident in one day? All right, so that's for somebody. There's another one coming up in a couple minutes. I'll tell you about that. I only noticed it a few minutes ago. What's the probability of no car accidents in one day? So the average number of car accidents in one day is 4.
Oh.
All right, so we're looking at the expected value being 4. So if somebody were to say that there are no car accidents on any given day,
yeah, that's another typo. This next sentence is another typo. What is the probability of one car accidents in 2 days?
Told me. Is that 3, George?
You got it.
Yeah.
in 2 days.
Accidents. I like that.
Yeah, that's wrong.
Yeah, this was the finish line for me. When I was copying and pasting, I just stopped.
You're so close.
Yeah, I was like, you know what, I'm not even gonna bother trying to fix anything anymore.
This
But
is stuff
it was also the finish line for students in the past, because we get to this part of the unit. There were so many typos prior to this that most people didn't even have to get to the last few pages in order to have their 3 typos for the marking period. So
You're just mocking us now.
yeah, I wish. Honestly, I wish.
Yeah.
Now, accident CE, that's not even a word, right?
No.
So that should have been underlined in red on Microsoft Word, but I don't recall that being the case, but I'm sure I'll be proved wrong.
It probably means something that we don't know. I'll look it up.
I'd like to think so, but I have a sneaky feeling it's not going to be the case. All right, so the solution, just a guided solution, pretty straightforward. X representing the number of car accidents on the highway in one day. Then we have X equals I. You know, if you're using your sequence notation, X and I, X represents a random variable. I represents the position within the random variable. So the first term, the second term, and 0th term if you want. All right, so here we're talking about f sub x, so a function of x, where we're evaluating it for a particular number I. All right, but in general terms, since we're talking about the average number of car accidents being equal to 4, that gives us a mu value of 4. All right, so and really, if you look at the formula, that's really all there is to it. All right, because if you have that value, then everything else is based off of the number of successes that you would want to have. Now, it's kind of weird to think of the number of successes as being the number of car accidents. I would imagine that if you considered a high number of car accidents as being largely a successful day, then I would say that you're just probably a pretty morbid person. But yeah, some of us are like that, and that's, I guess, human nature.
Accidents does actually mean something. It's the part of grammar that deals with the inflections of words.
Oh, okay. So at least I understand why it wasn't. I mean, it's not even remotely appropriately used here.
It did say in the definition that it is dated.
Dated. Okay, so it's archaic.
Yeah.
Yeah. So that's pretty terrible. All right. So if I want the probability of no car accidents in one day, and I'm looking for the probability that x is going to be equal to 0. All right, so it's not really bad when you think about it, because it's just a matter of plugging and chugging away. All right, so in our calculators, let me actually get my calculator out. Still ticking off, okay. In our calculators, there's actually a Poisson function. Poisson PDF.
Lambda.
Yeah, some use lambda, some use alpha, some use mu. It's just like everybody kind of took it and was like, let me just use whatever symbol I want. It's actually named after, I forget his name. I mean, his last name is Poisson. I just forget his first name. Something very Frenchy.
That's really okay. That's real. No.
All right, so calculator-wise, there's really nothing to it, because all you have to do is put in the mean and the number of successes, and you have your Poisson probability. Poisson. Oh. Oh. Very nasal way of saying it, if I remember correctly from my 5 years of French between middle school and high school, and the fact that my French was so awesome that the first time I tried to use it in France to order at a restaurant, I was told, Monsieur, s'il vous plaît, en anglais. And I was like, oh, okay, you're a jerk. And then that was it. So.
I think your most Parisians are jerks, and the rest of France is nice.
Yeah, I mean, just generally making that.
Take like a practice shot.
Conclusion, I guess, is kind of like saying that the worst drivers in the world are from Jersey, which is true. Second worst are
I think
from.
I found the text
Oh,
that
there.
she's talking
I've
about.
seen that.
Yeah.
Is that
Honestly, I feel like the further I get away from the tri-state area, the worse the driving is. I went down to just outside of Philly over the weekend, and as I got closer to Philly, the driving got worse. Like back roads, it was perfectly fine, but then as I got closer to Philly, it got worse and worse. On the way back roads were fine. As I got closer and closer to New York City, the driving got worse. It's just, I think it's just metropolitan areas, so it is what it is. But yeah, there are terrible drivers everywhere, and most of them drive Audis. So I apologize if you're an Audi driver. Actually, I'm only saying that because I feel like I have to say it. I really don't apologize. If you're an Audi driver, you're a bad driver. That's really all there is to it. Right? If you're a BMW driver, you're right behind the Audi driver in terms of being a bad driver. Surprisingly, if you're a Kia driver, you're right up there with the BMW and Audi drivers in terms of being terrible. So yeah, those are your trifecta. We will be doing a study in the second marking period where we're going to have to collect some data in the real world. I encourage people to try to prove or disprove my claims that it's Audi, BMW, and then Kia, one after the other.
In my experience, the worst drivers I've encountered were the ones who were driving moving.
Moving what?
Oh, now you're getting into a different class of vehicles. So
Yeah, you could also say that the most dangerous drivers are people with oversized loads. Because they take
yeah, they take up the entire highway.
the
Yeah,
entire highway.
that's irresponsible. I think Tesla drivers are kind of creeping up there.
I have not encountered.
Don't
some
insult
wild
the
Tesla
professor.
The Professor. Actually, he's a very good driver. But what he came to learn is that if you combine really cold temperatures with a low battery, the car just doesn't want to go any faster than a certain speed. So when you're driving, let's say on a back road in Vermont, trying to go skiing, and you're going uphill and you can't go faster than 12 miles an hour, and people are blaring their horns at you, they think you're a terrible driver, but you're just working with what you got.
I remember in business dynamics, in freshman year, MC was still like jokingly thinking of getting the Tesla, and he would always use that as his example. He's like, let's just say I, MC, get a Tesla, and the APR is this originally, but it's going to increase. But obviously, this is hypothetical. I would never do that, guys. And then next year, he gets the Professor, the beautiful.
He got the license plate before he got the car.
Are you serious?
Like he reserved the license plate. Professor. And he's been trying to talk me into getting a Tesla, and he researched to see if Tesla was available for the car.
Was
and it is available. And I really
Want to do it?
am like right there.
Yeah.
Like, there's a solid chance I'm gonna do it. All right. So did you find it? You found the typo on this page? Suppose the average number of calls by 104 in 1 minute is like I don't know who 104 is, but I'm sure he's a really nice guy.
Oh, I thought that was like by one in 04 in the afternoon.
Yeah, you'd like to think that. You might be somewhat shocked to hear that it was supposed to be. Suppose the average number of calls to 911 in 1 minute
By 104.
Last night, one of those calls.
is 2.
Why?
What is the probability of 10 calls in 5 minutes? All right. So what we have to do first is figure out what mu is going to be. Now, it says average number of calls in 1 minute is 2. What we're looking to do is find the probability of 10 calls in 5 minutes. So really, we're not limiting ourselves to 1 minute. We're looking at 5 minutes, right? Because that's what they're talking about in terms of the structure. So I have to find the expected value, mu. I don't know why I just did that. Mu over 5 minutes, all right? So over 5 minutes. It's a lot more visible, that color on this screen. It's not bad. All right, so 2 times 5 is going to be 10. All right. So when I'm looking for my Poisson probability, I'm looking for the probability that x is going to be equal to 10. So right at the average value. All right. I'll use. So you could just do Poisson PDF, but I'm going to write the actual expansion of it. All right. So again, just looking at the formula, And really, it's just a matter of applying the formula. We'll talk about where the formula came from Wednesday, but I want to get to hypergeometric a little bit today also. So e to the negative mu times mu to the I over I factorial. All right. So we're looking at f sub x of 10 is going to be equal to e to the negative 10 times 10 to the position within the function. All right, so to the 10th power over 10 factorial.
So you said we're going to learn to derive these in Cal?
Not necessarily this exact formula, but something very, very close to it.
Okay.
Because this is very similar. This is based off of a Taylor polynomial, the coefficient of that, and so you're going to get pretty much that coefficient of your Taylor polynomial. All right, so if we're doing it by hand, it's not that bad, but you know, knowing that you could do it on the calculator with really little to no effort is, you know, kind of thing that makes you not want to do it like this at all. But you know, I'm going to do it at least at one time. 10 factorial, math probability option 4, and so you get that about 0.125. All right, or you could do Poisson PDF, the mean, and the number of successes, and you get the same thing. All right, so about 0.125. All right, so not bad. All right, but again, without having the context behind like where this formula came from, not the most meaningful thing just yet. All right, so we are going to want to learn about what characteristics there are related to a Poisson distribution, what it looks like, you know, how the probabilities kind of work their way into it, and also how it relates to a normal distribution, because there's a lot of things that kind of feel like maybe a normal or binomial distribution would be appropriate, but for some reason we switched over to this Poisson distribution. And really, we're talking about the idea of rare events. All right, so if I'm talking about the idea that I'm going to make, or somebody, you know, I'm working at 911 and I'm getting 2 phone calls every minute, you know, like a rare event might be not receiving any phone calls, or a rare event might be receiving 100 phone calls in a minute, you know. So if it's some sort of emergency situation, you know, like some sort of catastrophic event, you know, thinking in terms of like an attack of some kind, you know, like something on that level, you know, like you can evaluate that sort of thing using probabilities. All right, it's pretty interesting academically to think about that. It's pretty disastrous to think about it in terms of the logistics. So the hypergeometric probability distribution. So this has a lot of similar characteristics to geometric distributions, except it allows for the without replacement component of it. All right, so discrete probability distribution describes the probability of k successes, all right, in n draws without replacement from finite distribution. Finite population size n that contains exactly k objects with that feature, where in each draw is either a success or failure. In contrast, the binomial distribution describes the probability of k successes in n draws with replacement, all right? Because we spend a lot of time working on cases that involved replacement. This technique allows for without replacement. So it's basically going to take you through the concepts of binomial probability just for situations that involve without replacement, right? And as we know, hopefully, the geometric distribution is really just looking at a binomial distribution from a different perspective, right? Because in a binomial distribution, you already know the number of trials, that's fixed. You know, 20 multiple choice questions, you know, or 15 free throws. You either make it or you don't, you know. Whereas if you're in my calc class, you're going to experience the geometric distribution today, or maybe you already did, where how many shots do you have to miss before you make one? All right, that's a geometric distribution. All right, a hypergeometric distribution talks about the fact that you can have without replacement situations work their way into this as well. All right, so you really got to think about under what circumstances that would make sense, because you wouldn't necessarily talk about multiple choice questions without replacement. So if I had 20 multiple choice questions and it was a without replacement situation, that wouldn't really make sense, because if I choose choice A, for example, for my first answer, without replacement would mean that I can't use choice A anymore. All right, so that would mean choices B, C, or D. I could only have, bottom line is I could only have at most 4 questions, because if I have only 4 choices, then I would run out of choices, right, without replacement. With replacement allows it to work, all right? So in a situation like this example, suppose there are 50 officers, 10 female, 40 male. Suppose that 20 of them will be promoted, all right? So this is a natural without replacement situation, because once a person is promoted, they're not gonna get selected again to be promoted to the same position. I mean, they could get promoted again, but if you're talking about getting promoted from, let's say, sergeant to detective, if that's the case, you're not going to be selected a second time to be promoted from sergeant to detective, because you've already been promoted from the one position to another. All right, so most people have kind of looked at this as like, all right, cards, dice, things like that, that's your with replacement, that's your binomial, stuff like that. You get into the real world, now you're talking about dependent situations, you're talking about without replacement. It's not as simple as just being, binom PDF, right? So this is the technique that you're going to use, and if you look at the structure of it, I mean, the formula itself is pretty intense looking, but it's really not that bad. We're letting X represent the number of female promotions. All right, so what we're doing is we're finding the number of combinations that we could have for female promotions, and the number of combinations for the 20 male promotions, and then the number of combinations for promotions overall. All right, so basically subcategories for promotions multiplied together divided by the number of possible promotions that one could have in general. All right, so when you think about it like that, it's actually not really difficult. It's just a matter of having an idea of what it is that you're looking for. All right, so 20 of them are going to be promoted, so that's the key. So, if we're looking to, you look at this situation here, like the motivation behind answering the question to begin with might be something along the lines of, well, what I want to show that there's maybe some discrimination going on. Like males are more likely to get promoted in this industry than females. All right, so that would be this is saying that none of the females are going to get promoted, and all of the males will get promoted. All right, so.
Well, no, wouldn't it be that all the promoted are males and not that all the males are promoted?
He's right.
Say that one more time.
You
He's
just
saying
said
it backwards.
He's saying that you said that what's the probability that all the males are promoted, but it would have been right to say all the promoted are males because there are 40 male officers, and since there's only
Oh yeah. That's what I meant to say. Yeah.
No, you're
So probability, all promoted are male. Right. Yeah, because if it was all the males promoted, then we would need 40 slots, which we don't have. All right. So yeah, makes sense. So this would be the general relationship that applies in this situation, all right? So it's just really a matter of applying it to any situation. But if you look at a population size, n, and k objects that have that particular feature, then you can start the process of generalizing it, all right? So what we're looking at here, if we're actually gonna make that generalization, you have n overall. So let me just find a nice place to put this. Yeah, you still have to be specific. I don't want to get too crazy with this. It's really just the total number within that characteristic, so I'll just say K. And then poor quality, parentheses. All right, and so we would need two entries that add up to n, and that's where you start getting other variables involved. So in this case, I would just say, because I have n as 50, the first entry would be 10, the second entry would be n minus 10. And then the second part is, I think, pretty obvious, because it's just going to be I and k minus I. But you need some particular value in order for it to play out, unless you want to define this as a new variable. All right, so this is the number within one category. All right, so I kind of, for this one topic, I mean, there's general rules and everything, but for this one topic, I kind of stay away from the general rules, just because it really kind of makes more sense to think about it in the context of the situation. Because I would say, all right, how many of each category do I have? And how many do I want from each category? All right. Now, if I were to compile it all or aggregate it all together, what would I have? And those end up being the three parts of your probability, right? So if I wanted to say something like, males and females are easy, even though they try to discourage us from kind of keeping it binary. It's just, it makes it easy to do the probability questions. But if I were to say freshmen and sophomores, and I wanted to know how many would be selected on some sort of athletic team, right? So from each category, I would look at the number of freshmen, number of sophomores, how many I wanted from each group, and then the total of freshmen and sophomores, and then the total number of available positions, right? And it's really as simple as that, right? So, see? Like, this is one of those situations where I don't know that a formula is necessarily needed. And you can see the general formula involves just a ton of variables. And you have to know what those variables mean, otherwise you're just making things more complicated. All right. So I'll skip the table for today, because I'll show you how to, when we talk about the Poisson distribution on Wednesday and where that comes from graphically, I'll also show you the hypergeometric. But I'm also looking at the clock. So the example here, we have 30 students, 20 male, 10 female, applying to the same college. All right, this college is only going to accept 10 students. What's the probability 5 of them will be male and 5 of them will be female? All right, now it's an overly simplistic type of situation, because really, if you think about it, like, yeah, I'm sure there's some kind of analogous situation to what you're going through right now. Like, you're applying to colleges, and there is potentially some college that multiple students in this school are interested in going to. And you would say, oh, wow, that school accepted 9 males and 1 female. That's not fair. But then, you go to the school next door. What's the one that's closest to this? What high school is closest? Richfield?
Richfield.
Somers, one of those schools, and it's the other way around.
Yeah, Somers is nowhere near here.
Well, it's closer than White Plains, which is where I'm from, so everything seems close. So
Somers is literally closer than Fox Lane.
I would say Fox
That's
Lane.
debatable.
So you got 3 schools in the surrounding area: Fox Lane, Somers, and Ridgefield.
Okay.
And it could be balanced the other way around, where you have 9 males and 1 female here, but then maybe it's 1 female and 9 females in Fox Lane. And then you have 5 and 4 in Somers, and and then you go over to Connecticut, Massachusetts, and you have an even split. So you don't really know from a small sample but this is the beginnings of a really useful study.
Over 10%.
So, my calculation, very simple, and kind of the reason why we don't have to go too crazy with this. We're looking for 5 from each group. So 20 C5. By the way, I kind of glossed over this. I hope, well, the hope was that you'd pick this up, but if you didn't, I'll just say it. This notation, folks, this is the same as writing 20 C5. All right, that's combination notation. It's on the AP formula sheet also. So it's something that they're kind of expecting you to know, but I didn't think it would be reasonable to not at least address it once. All right, so 20 from the males, 20 from the females, and then 10 from everyone. All right, so we just run these numbers. And unfortunately, in our calculators, it looks completely different. So math, probability, NCR, and it looks even more different in my calculator than it does in yours. So it's all
That
it
looks
is.
less different though.
This looks more consistent with this than it does in yours, but one day. This one I don't need parentheses for. So about 0.13-ish.
What?
Yeah, that kind of makes sense.
Yeah, it does.